Next chapter, Approximations and Errors. Now, an approximated value is one that is considered closer to the true or actual value. Approximations are made by either rounding off numbers to specific number of decimal places, significant figures, or truncating the numbers. Significant figures. Sometimes, and in many instances actually, when we do calculations, our computations give answers with very many digits. For example, the number on your screen. I don't know which instrument can give a measurement to this accuracy and how necessary that will be. We therefore express numbers in simpler forms using only the significant figures correct to the desired degree of accuracy. The rules governing significant figures include: first, significant figures are counted from left to right. Secondly, all non-zero digits are significant. Zero may or may not be significant depending on its position in the number. If a zero occurs in between non-zero digits, then it is significant. For example, 7052 and 7.204 both have 4 significant figures. If a zero occurs at the right end after a decimal, it is significant. For example, 5.0 has 2 significant figures. When a zero occurs at the left end of a number, it is not significant. For example, 0.245 and 0.0264 have 3 significant figures, both of them. Now this is where the problem comes. If a zero occurs at the right end of an integer, it may or may not be significant. For example, the number 760,000 could be correct to 2, 3, 4, 5, or 6 significant figures. When the number is expressed to 2 significant figures, none of the zeros are significant even though they are written. Conversely, to 6 significant figures, all the zeros are significant. On the other hand, the number 995 can be written as 1000 correct to 1 significant figure. In this case, only 1 is significant and the zeros are not, even though they must be written. Or the same 1000 correct to 2 significant figures. In this case, 1 and the first 0 are significant. The other 2 zeros are not, even though they must be written. Truncation is an approximation where digits are chopped off to a given number of significant figures or decimal places. For example, 0.5555 truncated to 3 significant figures will be 0.555. Truncated to 4 decimal places, it will be 0.5555. Rough estimates are used to find the approximate value of calculations. This involves rounding off numbers to given significant figures to make the computations easier. For example, give the rough estimate of 15.9 plus 7.2 over 9.83. Now we can approximate these values as 16 plus 7 over 10, and that will give us 2.3. Next, using a calculator. Now, a calculator is a simple kind of a computer that can perform a large number of mathematical operations. A scientific calculator is more advanced than the ordinary shopkeeper's calculator. This is a Casio make of a calculator, one of the models acceptable for use in high schools. An important feature is that the calculator must not be programmable. When you look at the calculator's buttons, there are functions written on top of them, like the numbers 0 to 9, the plus sign, the minus sign, the multiplication sign, equals, sines, cosines, tangents, and so on. This indicates the primary operation of that button. Above some of these buttons, there are yellow writings, and in others, somewhat pink-colored writings. These indicate what I can call the secondary operations of these buttons, like the cube root above the square root button, antilog above the logarithm button, and so on. On the upper left side, just below the screen, there is a button, and above it is written Shift. This button is pressed first to operationalize the secondary operation of the respective buttons. We will see that. I doubt if you will ever use the alpha button, so let's leave it for the moment. We see a few operations, and let's start with fractions. This is the fraction box here. I want to input 2/3 plus a quarter. The cursor is positioned on the numerator position now, so I press 2. To switch the cursor to the denominator, we use the central replay button. Press down and you see the cursor now moves. Now input 3. There is our fraction. Again, we use the central button to move the cursor to the right. We now have a full cursor. Press plus and use the fraction button to enter 1/4. So 1, move down, and 4. Now press equal, and there is our answer, 11/12. Now we will use this answer in our next calculation. We have 11/12 here, and I want to do 11/12. Instead of typing 11/12, we use the answer button located here. So 1 minus answer. Press equal and we get our answer, 1/12. Now we look at the brackets and we will do 9 plus 3 times 4. We clear the screen first by pressing this AC button. These are the opening and closing brackets. So opening bracket, 9 plus 3, closing bracket, then times 4, press equal, and we get 48. Now we do the square button, 4 squared. Press 4, and then x squared, then equal, and here we have 16, the answer. Next to the square button is the square root button. We will use that to calculate the square root of 16. Press the square root button, input 16 and press equal. We get 4, which is the positive square root of 16. Above the square root button is the cube root function. To access this, we need to press the shift first. Notice there is a small s in the top left corner. Then the square root button. We find cube root of 8, press equal, and we get 2. We do that again for cube root of 64. Shift, root button, then input 64, 6. I have accidentally input 65. So to correct my mistake, I use this delete function to delete 5 and then press 4. Equals, we get 4. We use the shift process to find the inverse of tangents, sines, cosines, anti-logarithms, and all the operations indicated with yellow. Keep practicing with your calculator. It can help you improve on your speed and accuracy, but if you don't master it, it can mess you up big time. Good luck. Next, accuracy and errors in measurements. We know that physical quantities are measured using different instruments. The accuracy of the quantity measured depends on the sensitivity of the specific instrument. The sensitivity of an instrument is determined by the smallest division on the scale. This is called the least count. Look at this straight edge ruler. This ruler is graduated in centimeters. So the smallest length that this ruler can accurately measure is 1 centimeter. If someone measured a given length with this ruler and gave results like 12.6 centimeters, this is misleading. There is no way you can get 0.6 centimeters using this ruler. With this ruler, any measurement must be rounded off to the nearest 1 centimeter. And so 12.6 centimeters will lie between 12 centimeters and 13 centimeters. The least count for this ruler is therefore 1 centimeter. Now compare it with this second ruler. The second ruler has 10 small divisions in 1 centimeter. Each small division is 1 millimeter or 0.1 centimeter. The smallest length that this second ruler can measure is 1 millimeter or 0.1 centimeter, and this is the least count for this ruler. With this ruler, it is possible to measure 12.6 centimeters accurately. So the second ruler is said to be more sensitive than the first one. And so when a measurement is given, you can tell the least count of the instrument used to measure it. For example, 19 kilograms means the least count was 1 kilogram. 19.0 means the least count was 0.1 kilograms. 19.00 means the least count was 0.01 kilograms. I hope you can relate the least count to the number of decimal places in the figures. Absolute error. Because there is no instrument that can measure with 100% precision, any measurement provided has what we call a rounding error, which has a negative and a positive sign. Rounding error of an instrument is equal to a half times the least count of that instrument. And so for 19 kilograms, rounding error will be equal to a half times 1, and that gives us plus or minus 0.5 kilograms. 19.0 kilograms, the rounding error will be a half times 0.1. That gives us plus or minus 0.05 kilograms. And 19.00 will have a rounding error of a half times 0.01, which gives us plus or minus 0.005 kilograms. When the sign in the rounding error is disregarded, then it is called an absolute error. Absolute means there is no sign. For example, find the absolute error in 25.04 kilograms, 30 degrees Celsius, and 43.0 millimeters. In the solution, A, 25.04 grams. Least count is 0.01 grams. Rounding error is a half of that, which is a half times 0.01. That is equal to plus or minus 0.005. We disregard the sign and give absolute error as 0.005. 30 degrees Celsius, least count is 1 degree Celsius. Rounding error is a half times 1, which is plus or minus 0.5. Absolute error is equal to 0.5. Finally, 43.0 millimeters. Least count is 0.1 millimeters. Rounding error is a half times 0.1, which is equal to plus or minus 0.05, and absolute error is 0.05. Next, relative error. Relative error is the ratio of the absolute error to the actual measurement. And so for the above, 25.04 grams, the absolute error is equal to 0.005. Relative error is equal to 0.005 over 25.04, and that gives us 1.996 times 10 to power negative 4. 30 degrees Celsius. Absolute error was 0.5. Relative error is equal to 0.5 over 30, and that gives us 0.0167. Percentage error is the relative error expressed as a percentage, and so percentage error is equal to absolute error over the actual measurement times 100%. For the above, percentage error in 25.04 grams will be equal to 0.005 over 25.04 times 100, which gives us 1.996 times 10 to power of negative 2. Percentage error in 30 degrees Celsius is 0.5 over 30 times 100, and that gives us 1.67%. Next, propagation of errors. Now, when measurements are used in calculations, the errors in them are passed on to the solutions. This is propagation of errors. Let's see the maximum and minimum values. Now, to obtain the maximum possible value of a measurement, we simply add the actual measurement plus the absolute error. For example, the maximum possible value of 27.2 centimeters, least count is equal to 0.1 centimeters, and so the absolute error will be half of this, and that is 0.05 centimeters. The maximum possible value, also called the upper limit, will be 27.2 plus this absolute error 0.05, and that is equal to 27.25 centimeters. To obtain the minimum possible value, we subtract the absolute error from the actual measurement. So for example, the minimum possible value for 27.2 centimeters will be 27.2 minus the absolute error 0.05, which gives us 27.15 centimeters. This is also called the lower limit. Addition and subtraction. Find the maximum and minimum values and error in the following: 2.4 meters plus 3.55 meters. The absolute error in 2.4 meters is 0.05. By now I hope you can see where we are getting that from. And so we set the limits for these measurements, that is the upper limit and the lower limit, will be given by 2.4 plus or minus 0.05. Again, the absolute error in 3.55 will be 0.005. The limits will be 3.55 plus or minus 0.005. The maximum possible sum, we add the upper limit. And so 2.45 is the upper limit for 2.4 plus 3.555, the upper limit for 3.55, and that will give us 6.005. Minimum possible sum, we add the lower limits. So we have 2.35, the lower limit for 2.4, plus 3.545, the lower limit for 3.55. That will give us 5.895. The actual sum will be 2.4 plus 3.55, and that will give us 5.95. Now the error is calculated either by maximum minus the actual measurement or actual measurement minus the minimum. If you do both, maximum minus actual will give us 6.005 minus 5.95, it's equal to 0.055. And again, actual minus minimum will be 5.95 minus 5.895, and that is also equal to 0.055. And so we say the error in the addition of these two is 0.055. Now notice that the error in the sum is equal to the sum of the individual errors. You do not have to do all these calculations to get the absolute error. If we had added the individual absolute errors, we would still obtain this answer we obtained at last. The absolute error for 2.4 was 0.05 plus the absolute error for 3.55 was 0.005. And if we add those two, we get 0.055. And so when required to give the error, you do not have to do the addition. You just add the individual absolute errors. Now, let's find the maximum and minimum values in 6.4 kilograms minus 2.93 kilograms. Observe carefully how we go about minus. The absolute errors, 6.4, the absolute error is 0.05. By now you know how we are getting that. And so the limits of that is 6.4 plus or minus 0.05 kilograms. 2.93, the absolute error is 0.005 kilograms. The limits, 2.93 plus or minus 0.005 kilograms. Now, to get the maximum possible difference, we do maximum possible value minus the minimum possible value. And so we go for the upper limit of 6.4, that is 6.45, but we subtract the lower limit of 2.93, that is 2.925, and that will give us 3.525. Next, minimum possible difference. Now in this one we do the opposite. We subtract the minimum minus the maximum. And so we go for the minimum possible value of 6.4, and that is 6.35, minus we go for the maximum possible value of 2.93, and that is 2.935. We subtract that, we will get 3.415. The actual difference is 6.4 minus 2.93, and that is 3.47. The error is given by maximum minus actual or actual minus minimum. So maximum minus actual is 3.525 minus 3.47. That gives us 0.055. Actual minus minimum will be equal to 3.47 minus 3.415, and again that is equal to 0.055. So you can do any of them. But again, you notice that the error would have been obtained by simply adding the individual absolute errors. That is 0.05 plus 0.005 to still give us 0.055. And so the error in the difference is the sum of the individual errors. Next, multiplication and division. Now the absolute error in multiplication and division is given by absolute error is equal to a half times maximum value minus minimum value. For example, find the percentage error in the area of a rectangle measuring 12.3 centimeters by 9.6 centimeters. Absolute error in both is 0.05 centimeters because both have one decimal place. The limits are 12.3 plus or minus 0.05 and 9.6 plus or minus 0.05. Maximum area, we multiply the upper limits. 12.35 times 9.65. That will give us 119.1775. Minimum possible area is equal to, we multiply the minimum or the lower limits. 12.25 times 9.55 gives us 116.9875. Absolute error is a half times the difference between these two. That is 119.1775 minus 116.9875. That will give us 1.095. Actual area is equal to 12.3 times 9.6, and that is 118.08 square centimeters. Percentage error is equal to absolute error over actual measurement times 100%. If we do that, we shall get 0.01%. Another example, find the absolute error in 6.4 divided by 2.3. Again, observe carefully how we go about this one. The absolute errors in both is 0.05. Limits 6.4 plus or minus 0.05, 2.3 plus or minus 0.05. The maximum possible value for this division. In this case, we divide the upper limit divided by the lower limit. I hope that makes sense to you. And so we choose the upper limit for 6.4, that is 6.45, divide by, we choose the lower limit for 2.3, and that is 2.25. If we divide that, we get 2.8667. Minimum possible value for that division. In this case, we divide the minimum divided by maximum, or the lower limit divided by the upper limit. So we choose the lower limit of 6.4, and that is 6.35, divide by the upper limit of 2.3, and that is 2.35. That will give us 2.7021. The absolute error is equal to a half times the difference between the maximum and minimum values, and that will give us 0.0823. And finally, evaluate 19.43 divided by 6.1 and give your answer to the suitable degree of accuracy. Now, the suitable degree of accuracy is the number of significant figures in the least accurate of the two numbers. In this case, 6.1 is less accurate compared to 19.43, and so we divide normally and then give the answer correct to two significant figures. 19.43 divided by 6.1 is 3.1852. Two significant figures will give us 3.2.
I think one of the problems with math is if you aren't strong in it, you end up with weak spots in the foundation. And so if you want to build on that, if you want to go in and major in it or to do honors in it, you really do need a solid foundation. And so if you don't have it, if you've had a bad experience with math, you tend to sort of slough it off, and that's a serious mistake, I think. I believe with the right resources and help, most people can learn most of the math that they need to learn. But in almost any class that you go into, you need to make sure that you're at the starting point. People come in with different backgrounds, different preparations, and so you're not all on the first day at exactly the same place. And so you can go on and learn math. You may need tutorials, you may need tutors, etc., to get your foundation solid so that you can build the next course on it. But math is not so complicated that most people can't learn high school math and certainly the introductory courses in university.